Melina Jefferson just finished her Master's of Applied Science in our lab at Carleton University, is now the project engineer running the lab during these large-scale collaborations with partners from, well, all over the world. And we're very pleased that she's going to talk about work that she recently completed as part of her Master's. Thanks, Melina.
Great. Thank you again, everyone, for being here. Oh. I'll skip over the clapping. As Dr. Johnson said, I'll talk a bit more about flaring at hydraulic fracturing sites and any implications those may have. So a little bit more about what hydraulic fracturing is. Here's a little schematic about hydraulic fracturing. So typically, high-pressure fluids are injected into deep well bores. This is not to scale. The high-pressure fluids crack open the formation, allowing gas or oil that's trapped in there to flow to the surface. However, prior to the production stage, the well must be cleared of the fluids that were injected in a process called flowback, or a well completion. Typically, those fluids are brought back, when they're brought back to the surface, they're sent into separation tanks, whereas the name suggests they separate into their respective phases. Sometimes the gas phase is sent to a nearby pipeline, which is an inline or green completion, but more typically, they're just directed to a flare and burned on site. So here's a real-life picture of a hydraulic fracturing site. These black tanks here are the hydraulic fracturing fluid storage tanks. So there's about 20 or 24 tanks there, and you see how large those are. Those are probably like 150 to 200 cubic meters per barrel, or per tank. So we're talking a very large amount of hydraulic fracturing fluid that is injected into these wells. These red trucks here are pump trucks. So these are the trucks that are injecting and bringing back the hydraulic fracturing fluid from the well. So a little bit more now about the actual flowback process. You can see the wellhead that was in the previous picture and then the pump trucks in the background. You can actually even see the tanks there as well. So the fluids are brought back from there, and following the yellow arrow here, the fluids are sent into the separation tank, and then the gas phase, again following the yellow arrow, is sent to the flare. So our main concern here is that if there are any liquids that are not fully removed during the separation stage, there's some anecdotal evidence that this is happening. Operators sometimes can't keep the flare lit. There's so much liquid coming out the flare stack. And also that white tank there beside the flare line is a line heater that's meant to keep lines from freezing. And the only reason to keep lines from freezing is if there were liquids in there. So this is an important thing to be looking at. And indeed, this is somewhat in the regulations now. There's one regulation by the Alberta Energy Regulator in their Directive 60 that says droplets greater than 300 to 600 microns must be removed during the separation stage. The spirit of this regulation had nothing to do with the aerosols we're interested in, nothing to do with the flowback fluids. This is to prevent any combustible droplets from not fully combusting in the flame and then having burning rain come down and light the province on fire. No actual regulation on any flowback fluids in these lines. But very recently, just this past fall, the Alberta Energy Regulator started this flowback technical committee, which was rather shy on the technical component. So we've inserted ourselves and said, let us help. And so we're trying to influence sampling protocols and maybe steer this in a direction that is, we think, of real importance. So initially, this campaign was meant to just sample the flare gas at the hydraulic fracturing site. So just the gas phase. We've tried to influence and look at maybe what those aerosols could be if they're getting through the flare. So do sampling of these aerosols, getting composition, maybe droplet size as well. And our expertise on sampling protocols would really help this technical committee. So in this process of engaging ourselves into this committee, it's been a bit politically challenging, not only just for helping out, but also getting access to sites to do these measurements ourselves or with Alberta Energy Regulator. So we did have access to one site very recently, just this past March. It's a bit dark here, but you can see the flare up on the left. We did some black carbon measurements, which will be discussed a bit more in the next talk. And you can see we will talk a bit more about how we measure black carbon with 2 tripods and a couple cameras and about 4 months of math. Okay, so what kind of hydraulic fracturing is going on right now? This red line here is water-based fracturing, which is called slick water fracturing in the industry. This is typically about 80 to 90% water, and the other component is some mishmash of chemicals and sand. So this type of fracking has been very popular in the last little while, and this led to some governmental pressure and public pressure for companies to disclose what kind of chemicals are being used in this hydraulic fracturing. And this led to FracFocus. There's FracFocus.ca for wells in Canada, FracFocus.org in the US for states that produce oil and gas. So what this site is, it's a public chemical disclosure website. So anybody can go to this site, find a well in your area, click your province by well ID or location, and find an individual PDF per well. In a very inconvenient format, it's an image-based PDF, so it's very difficult to actually extract data from that. And the quality control on those data sheets is somewhat suspect. Sometimes the total percentages doesn't quite add up to 100. Also times the chemicals that are listed are proprietary or trade secret, so you don't really know what it is anyway. So generally some problem like that, but maybe it doesn't matter, because what comes back up in the flowback is definitely not what goes down. So I've plotted here concentrations of the highest species that were found in flowback. This is from 29 sites across North America. You can see that at the beginning, which is time 0, the hydraulic fracturing fluid, by about day 5, the concentrations has spiked and then settled off by about day 5 to 10. So why is this changing? Well, there's already water in the ground, which is called formation water. This is usually very high salinity, and indeed, this plot on the left here is formation water from 600 sites across the world. It's also high in salinity, chlorine, sodium, and as you go down the list, it's dropping an order of magnitude. So taking those two plots together, the black dots are representing flowback from the previous slide. The red lines are the interquartile range of the species that we're looking at. The flowback is basically formation water at day 5 onwards. So what this literature survey basically told us is that if any aerosols are getting through the separation stage and directed to the flare, they are very likely high in sodium and chlorine. So what do we do about it? Our first step is to start conducting experiments in our nice controlled lab area. And we're injecting our lab flare, or our lab scale flare, with aerosols or liquid droplets that would maybe be found at the site. And can we provoke an effect? Are we seeing any change in flare emissions from that of a dry flare? You may saw some of these pictures earlier, but this is our flare facility here at Carleton. We can flare any custom mixture of gas right now. The mixture we used in our preliminary experiments was an alkane mixture of methane, ethane, propane, and butane that's representative of an upstream oil and gas mixture that would actually be seen in real life. The droplets we injected were about 20 microns in diameter, which is lower than that regulation. So this droplet size could be getting through, and there's no legislation that say it can't. Here's a new or a schematic of the lab that maybe shows a bit of a better understanding of how we operate. So our flare gas is injected into a pipe that goes down into a concrete pit where our burner is. Our aerosols are injected inside the gas phase before it's ignited, so it's fully mixed there. Above the flare is a large fume hood that collects all the combustion emissions as well as the ambient dilution air. And downstream, we measure our gas phase products as well as solid phase, like soot particles. Right now, we are capable of measuring carbon monoxide, carbon dioxide, methane, NOx, soot mass emission. And a new instrument we have is a PAS-3, which measures optical properties of the particulate. Our initial experiments first tested different types of two types of water, distilled and tap water, which are just minor contaminants, hydrochloric acid solutions, and 2 sodium chloride solutions. So jumping right into the results, hopefully this doesn't get too in-depth here. I'd like to show carbon monoxide first. So the y-axis on this plot is the yield, so that's mass of carbon monoxide that's produced per mass of the flare gas that we burned. And on the x-axis is the liquid loading, so percent of water in the flare gas, the total flare gas that we burned. So takeaway from here is that as we inject distilled water, that's the blue lines there, but a 25% decrease in carbon monoxide. With the acid solutions, these two, the green on that, we see maybe an interesting competing effect between some chlorine and water effects. However, most interesting effects happen when you inject salt. So I'd like to point out the change in scale of those two charts, and those lines there are these lines here. So when we inject 15% NaCl into this flare, we see over a 25-time increase in carbon monoxide yield. And with the smaller concentration, we saw about a 7-time, but certainly significant increase. Something else interesting with the gas phase emissions, so that CO yield was the chart that I just showed in the previous slide. The methane yield is somewhat proportional to this to the CO yield. We actually saw no methane, no unburned hydrocarbons, basically, with any water or acid test. We only saw methane when we injected salt. But that these two are proportional shows that when we inject salt, the way it's affecting the flare is it's not causing any unburned fuel. It's not stopping any combustion process from happening. We're only just partially completing it, which is maybe more interesting and more concerning. So a little bit now about the solid phase particles, or solid phase combustion products. The chart on the left shows what we typically saw when we injected water and acid. This chart shows basically that we see a decrease in total particulate. That was as expected. We talked about steam and air assist, or Dr. Johnson talked about steam and air assist earlier. It's a very standard practice to reduce visible sooting. So this is generally as expected. Again, when we inject salt, we see a more significant and opposite effect. Again, note the change in scales between these two plots. Very large increase in total particulate that we're emitting. And perhaps not only are we emitting more particles, maybe the particles themselves are changing. So the plot on the left here shows some optical properties of the soot when we inject with a standard dry flame. That's the black dot, and the blue and green lines are the acid. Basically, over the liquid loading and between those different types of liquids, we don't see any change in the type of soot that's being emitted. So maybe we're seeing less soot as we inject more water and acid, but the type of soot that we're creating is the same. Not the case with the salt solution. So we see the significant changes depending on concentration and liquid loading. We don't really understand what particles we're creating yet, but we do know that they are not standard soot particles. And that could have serious implications, as Dr. Johnson was saying. So this is the figure that's been shown before. So that's a standard soot particle on the left, small primary particles of soot in a nice aggregate. When you inject NaCl, we could be seeing particles like this. So these parts are the same carbon. Then you have these large actual crystals of salt inside the particle. We have no idea what this means or what it does or how many, are all the soot particles like this or some not? Is this a fluke? So there's lots more to be done to figure this out and have a more clear idea of what's really going on with the soot. We also know that chlorine could have an interesting effect on the gas phase emissions. It could promote incomplete combustion, which could be causing our increase in methane and carbon monoxide yields. So to conclude my rather hurried presentation, our goal for this initial test in year 1 of FlareNet was just to see if we could provoke an effect. Can we do anything that actually changes the flare emissions? And certainly, yes, we were. Most significantly with the NaCl tests. First, we saw an increase in carbon monoxide up to 25% with the conditions we tested. We saw that salt increased the total particulate that were emitted. And not only increasing it, but we're actually changing fundamentally what particles we're emitting. And we don't really quite understand what we're changing yet, but to be continued. We will figure it out. So this has real potential implications for actual flowback flares. Certainly the results from this preliminary test were interesting enough that warrant serious investigation. This brings in the field work we need to do and more lab work. Basically brought more questions than answers, but that's what good science does. So our future work, I just mentioned, we'd like to continue working with AER in their technical committee, get more access to field sites, do our aerosol sampling, get a true idea of what's really happening in the real world, and then we can take that, bring it back to the lab, do our controlled experiments, and try to understand fundamentally what's happening in the flare. We'd also like to do some extractive sampling for certain species or particulates that we can't really do in-house. So that's another whole ballgame of sampling protocols and making sure that we're designing our experiments and our protocols in a defensible way so that we can provide the science for this science-based regulation. And as Dr. Johnson said, it's really important for us to do this properly and have defensible data so we can really make a dent on the needle of flaring and maybe what we're actually producing. So here's the slide of all of our collaborators. I won't repeat them, but we'd like to thank them all for their support. And if anyone has any questions, we've got probably lots of time. Yes?
That's really interesting and important work. Because, as you said, we don't know the cocktail, the chemicals that go in the cocktail that go into the ground. And so now you identified salt water as being
Yes.
very potent. Now, can you track it back to potential chemicals that are used in that cocktail?
Well, we aren't really understanding, we don't have a very clear idea of what's injected into the ground. So you want to know if we can somehow relate the salt content to that, to what's injected? I don't think it's related at all. They mostly don't inject. Concentrations of salt in the injected fluid is very low. So all of the salt we're seeing is from the formation water, which is usually supersaturated brine. So it's contributing pretty much all of the sodium and chloride. There's some stages of fracturing. It's not just one injection. Sometimes they do an acid wash first. So they put a high concentration of HCl in, bring it back up, then do the fluids. So certainly in certain stages, there could be different concentrations, but the literature and the data that I found has overwhelmingly suggested that it's primarily because it's just diluted with the formation water. So chemicals that we're putting down for our study doesn't seem to really, not that it doesn't matter, but it's overwhelmingly dominated by the formation water.
Okay, so it's not a combination of chemicals that might form reactions that will dissolve.
Certainly that is happening. There's some studies have looked at trying to map, so they know how formation water reacts based on old seawater data, so they know how evaporation and saturation curves, they can figure it out. And flowback water is almost exactly that, but not quite. So there are certainly some chemical reactions happening, whether that's between the hydraulic fracturing fluid and the formation water, or between the formation geology itself and the hydraulic fracturing fluid. So it's very many things going on, but again, it's very dominated by physical dilution of the formation water that's there. And there's, it's a lot of water that we're talking that we're bringing back up. So very heavily diluted.
Excuse me, why they use chemical with the hydraulic flow? Why they don't use just water?
Oh, that's a good question. So there's actually tons of ways to hydraulically frac. I think the very first frac was with propane or oil or something. There's many different ways, but it's usually so that when the fluid is injected, they've cracked. They basically need to hold the fractures open when you put the fluid down and you've got these fractures, and then there's little sand particles they usually put in to keep it open. But it's a very interesting process of how they actually make sure the sand particles are getting into the crack and holding it open. So certain fluids need to have certain viscosity to actually carry the sand particle to the crack. And it's very actually interesting industry of how they do this. It's a very interesting thermodynamics and fluid dynamics going on here. But basically they need certain types of fluids to make sure that the sand is getting to opening up the racks. And with slick water, I think they time it so there's actually different viscosities at different times during this hydraulic fracturing process. So I didn't answer that very well. I can maybe do some more research and get back to you on that, a bit more about that. But there's many things at play. Or maybe Dr. Johnson has a comment on that.
Pressure that they use.
Pardon?
How much the pressure that they need to make this?
Ooh, it can vary several orders of magnitude depending on what kind of geology is going on. We're talking thousands of pounds of pressure and up. Yep.
Yeah, I guess I have one question. Okay, so I can't remember if you or Dr. Johnson that was talking about, so in the AER regulation, droplets,
300 to 600 mics?
600, and in your test you did 19, I think?
Yes, yeah.
And so I guess my question is, like, where does that 300 to 600 number come from?
It's the American Petroleum Institute, API 521. They're a standard organization. They don't legislate. They just create a standard and then governments use that number. So the US uses that, we use that, Alberta, Saskatchewan, and BC all use that same standard. The range is because basically the spirit of legislation was to say that if you have a fuel droplet, a liquid droplet that's getting there, we need to make sure that it's fully combusted as it leaves the flame front. So if you have an itty bitty flame, like a really small little flare, the droplet size must be smaller for it to fully get through. So the droplet size, it's not very clear on how you choose what number you would like to use, which is another issue altogether. But larger flares, you could have a larger droplet and it would still be safe. Smaller flare, smaller droplet to still be safe. But it has almost nothing to do with non-hydrocarbon aerosols. So it's just conveniently somewhat talking about the same thing, but not really.
I think if I may, it's really good question. The idea was there is this regulation, whether or not it's being followed. And so we wanted to start with something well below the cutoff.
Right.
And as that would in current situations, that would likely be carried through flares. And does that have an effect? And if that did, then we could start worrying about droplet size. Melina didn't, great talk, but one of the clear goals is we think there's an issue here. What can we do about it? And so what would the regulation look like that would, avoid these situations? And maybe it's tied to droplet size, maybe it's tied to knockout. And so starting with this size that we're pretty comfortable is getting through knockout systems, I kind of secretly hoped we wouldn't find anything here and then we'd get to bigger and bigger droplets. But no, we've got something here, so now we'll go smaller.
Yeah. There's also the logistical challenge of actually doing this in the lab. There was many weeks of fun trying to figure out how to actually make sure the aerosols were getting into the flame and not just falling out or falling back into the droplet, into the burner. But we have in the works a new system that'll be injecting much smaller droplets. So I did test some droplet sizes, but the difference between the sizes didn't really show anything. So we're hoping to try a much larger range in the next year or two. So.
Yeah, quick follow-up, sorry. But, I'm not an engineer, so I have these naive questions.
No, not
The formation water, I'd like to ask a follow-up, because what is interesting from an economic point of view is the lifetime of the well. And how, what I would be interested in, do you have any insights how, as you pump more water through the system and the formation water changes, I guess?
On a big geological scale, you mean?
How would the water salt concentration change over the lifetime of the well? Is there, because it might influence how you regulate the well itself.
Oh, yes, absolutely. So I'm not a geologist, but I feel like we should probably be bringing in some expertise at some point in this. So you could have a geological formation here and one over there, and they could be somewhat linked, but totally different geology. So this could have maybe this is high in calcium carbonate or KCl rather than NaCl. So I think there's always somewhat linked. So I don't think you could ever deplete the formation water. It's very large volumes. Kind of speculating here.
But does the water concentration change as you?
I don't think so. So at least from the data that we've found, maybe we don't have enough data yet. We have data from Flowback and single point formation waters. So it would be interesting to do a formation water test before a frac, formation water test after frac, and over the years as fracking would continue on a well multiple times throughout its 15 to 30 year lifespan.
Yeah, I think people have looked at those kind of changes, but the issue here is more shorter duration. So a typical flowback will last days to weeks, maybe a month. And so really what you're concerned is during that month where you're flaring really quite large volumes at high rates and you have the potential to carry these liquids, it's just during that month. After that, when you go to production, it's slower rates into pipelines, you're hopefully not flaring. So it's, yeah. Great. Thank you, Melina.
You're welcome.